I guess we start now. So thank you everybody for joining my talk. I'm Moukarram, and I'm here to tell you about our experience in developing a complete IoT platform in the last 6 years using almost only serverless technologies. Before I start, I need to ask some questions just to understand like your level of experience. So who have used any cloud products? Okay, that's very good. And who's used AWS? Okay, that's like almost half of you. And who has used a Lambda or any other serverless product? Okay, almost exactly the same half, so which is actually good. So everybody who's using a cloud or using an AWS has touched at least a Lambda once. Before I start with the talk, I need to introduce the company I'm working for, that because we are hiring, which we are, but because that's a very important factor to understand how that started and how that the history of the company has affected the choice of technology we have made. So I work for a company called Sense and Guard. We started at a bigger company. It's called Grohe, which is, you may have heard of it, for creating sanitary products like water faucets. You can see a lot of them in the bathrooms here in the hall. And we started with 2 products you see on the screen. The first big one above is called Guard, which is some device you install in the water pipe. It monitors your water withdrawals, and it's also detect anomalies in case you have a big water withdrawal, or for example, you have a leakage, a minor or a big one, like dropping somewhere. It can detect that. It will shut then off your water supply, which means it will prevent having damages. The 2 devices, or the 3, but it's the same one, the Sense and the button, is called Sense, and you can put it where you expect water to leak, and whenever it detects water, it's able, of course, to notify you, but also to communicate with a bigger device to shut off your water, which means also it prevents having damages. Both these products, so may you have understood that they are IoT products. You connect them to your network, and you're able not only to control them, but they are also able to communicate and to prevent having damage at your home. These were the first 2 digital products at the company, which means when we started, there were no teams for developing software, no operations team for having like a digital product, and that's why we had to look for a way where we can develop such product using external companies, using like building up the team while we are going, but also if we could save or avoid having like an operation team, or if we could use some technologies which help us do the same work with less people, we would have opted in for that product. These products were launched in 2017. Development started 2016, and 2017 the first product was available on the market. From the beginning, we have used AWS for 100%. There is nothing at all running in any on-premises solution. Everything is cloud-based. Currently, the solution as it is right now, it handles 288 million MQTT messages. MQTT is a PubSub protocol used for low-footprint IoT devices. It's the one also supported by IoT Core, which is an IoT service from AWS, and that's why we use it. These MQTT messages and other actions are responsible for triggering more than 1.6 billion actions, which means we have every month more than 1.6 billion Lambda calls somewhere triggered either by an MQTT message from a device to the backend or from some other events which happens like regularly or something else happens. And as I said from the beginning, we went all in for serverless. Everything that was possible at that time to be done with serverless, we did it with serverless. Everything that was not possible, but later was, because of change in the platform or some new product, we opted in and we exchanged that part of the system. To understand what is serverless, so like you can find a lot of definitions of serverless, and almost all of them are wrong. So I prefer to take this take on it. It's called traits of serverless, which means like some kinds of characteristics. If you see them, you can expect that technology to be a serverless one. The first trait is you have no managing of a long-lived living application or host. You don't have an application server. You don't have a process which you started one, and then it runs for a few hours. Everything you write to react to an event. It's also limited in the time how long that lives, and then it ends. If you are using like a serverless database, you just write something to it and it works. You are not responsible for having something running anywhere. The second trait, it's auto-scale and auto-provision. It means like auto-scale, you create as many instances, as many processes as needed, like behind the scene. You don't have to worry about them. And also, you don't have even to provision a virtual machine for these processes to run. Everything is being managed for you. We will see, of course, later that although it works very well, it doesn't work all the time, or it has some limitations, and we'll see how to work around them. A very important aspect of serverless is that it has a very precise cost model. That means if you use it a lot, you pay more. If you don't use it, you pay less, and that goes all the way down to zero. If you don't use it, you don't pay anything. Like it's not similar to a web server where you have something running and you have to pay for it regardless whether you use it or not. If you don't use it, you don't pay for it. We will see later, sometimes that doesn't work well, so you have to opt in for a model where you pay per hour. But we will come later to that point. The fourth characteristic is performance. Capabilities are monitored or measured in terms other than host size and count, which is like if you have a database and your performance measurement is the size of the machine, that usually doesn't tell you how well that handles data. Like you can say, okay, if it's a big machine, it's probably a good one. If, I don't know, increase the RAM, it will be better. But that's not describing precisely how the performance you are getting out of it. Whereas in serverless technologies, usually you have a better measurement. So if we are talking about Lambda, which is running code, the performance is milliseconds, gigabyte milliseconds, which means like a number of milliseconds on a specific processor, or like a specific processor size. If you are talking about a database or like DynamoDB, this performance count is read or write units, which means like the number of kilobytes they are divided in units. I think 5 kilobytes. Like how many of these kilobytes you are reading or writing per second. That's a performance measurement you use for serverless technologies, and that goes also for other products. And also it has high implicit high availability, which means like you don't have to take care about scaling it, but it's also there. Like if you need more will be there. If you started, let's say, an instance, it has an error, it's faulting, you don't need something to restart it. It's there. Like if you have a Lambda which has an error, the next request which triggers a different Lambda, it will start from the beginning. It has a high availability which you don't need to take care of. So let's see now, these are the characteristics which, like I said, properties, when you see them, you can expect to have a serverless product behind them, but what does it actually mean? Like, what are examples of serverless technologies? And for that, you can recognize a pattern in, at least here in AWS ecosystem. Usually you have two flavors of a service. One which is has been completely developed for the cloud. It's a serverless one. It has some limitations, but it has a very high performance, very high throughput. And other is, you can say it's your traditional product which has only a managing product behind it, which like you don't need to patch the operating system it's running on. You have your known API, which you are maybe already using in on-premises solution, but it's being managed for you. If we take the server or the database example, so on the serverless side, you have a product called Aurora Serverless, which is a database which has been implemented completely from scratch for the cloud. It has very good performance. It has high availability. It has replication per default. It has like a lot of services. And then you have your RDS, which is like your traditional database server, which is only managed for you. It can be Postgres or any other product you are using already. It's exactly the same API. It's just like you don't have to take care of patching the operating system, but you have to choose where to run it on which virtual machine. So you are responsible for scaling it out, scaling it down, and everything else. The second example is queuing messages. So on the serverless side, you have SQS, which is simple queuing service, which means it's a product which again has been developed completely from scratch to work in a cloud environment. It has very good performance. It has some of the limitations, or or you lose some of the guarantees you usually have with a queuing product. So, for example, it doesn't have a first in, first out per default. You can't opt in for it, but you have to pay in performance. It has at least once delivery. Like it could happen, not very often, but it could happen that one message is delivered more than once. Like and you have also some other limitations, very minor. If you know how to work around them, you will get like a very cheap product with a very good performance. On the other hand, you have Amazon MQ, exactly. So it's like the managed active MQ product, which is exactly the same one, you know. Again, you choose a virtual machine to run on it, but you don't patch operating system. The third example, if you have a data lake or a big pile of data in files, and you want to query them, again, you have two ways of doing that, at least two ways, but the most important ones are Athena, which is, again, serverless product. You write your SQL queries to query this data. Again, you don't you don't worry about the infrastructure where it's running. It just runs for you, gives you some results, but it also means you don't have control over it. So if it's like a big query, it can take a long time. On the other hand, if you opt in for having more control, you can use a Redshift Spectrum, which doing very similar stuff, but you have to choose the virtual machine you run the product on, which means if you know this query will take too long, you can choose a bigger device or a bigger virtual machine, and you are in control for that machine, so you may have better performance. And last but not least, and now we come actually to the product which I will be talking about most in this talk, which is how to run code. Again, you have either a serverless product. I mean, there are probably 100 services to run code on any cloud provider. But in this case, the most prominent examples are the Lambda, where you can provide a piece of code in a language you like. There are like many options, but you have to choose one of these. You provide the code for that Lambda. You provide the triggers for that code. When do you want to run that code? We will see later a few examples of how to, or which kind of triggers there are. And then it runs. Like also you can provide, say, I want to have that much memory, which also influence the processor which will be running off. So you are a little bit in control for where it runs, but you don't have to worry about any of that. Whereas EC2, it's elastic computing something, I don't remember what. But anyway, it's like a virtual machine. You choose the processor, you choose the memory, you choose everything, and you're responsible for everything, from updating the operating system to installing software to keeping updated and everything else. Okay, so now we have seen a few examples of these products, and like there are hundreds more. So it's not like only these few ones I mentioned. So the most important one is of course the Lambda, because that's the one you can do the most with it, or that's where your logic will reside. But there are hundreds of services which qualify as serverless. But now we have these services and we want to write an application. How do we do that? The first step, and like I would say, just divide the workflow into simple steps. I mean, it's of course the hardest step in all these approaches, but it's and we'll see later that you usually have to do that anyway. Like, it doesn't matter how you implement your software, But when you're doing that with serverless technologies, you have some limitations which you may need to consider already at the beginning. But anyway, you want to do something. The first step is divide that into simpler steps. And then every one of these steps will be implemented via serverless technology. Either it's code to run in Lambda, it's some data to store in DynamoDB or something similar. Lambdas can be used in this scenario for two aspects. Like you have your logic, so that's actually the code you write to do your business logic. But also they can be used as a kind of glue between other services. So for example, if you have a message arrive from a queue and you want to write that into, maybe validate that message and then write that into S3, you have a Lambda to do that. If you, for example, have an input coming from a file system from S3 where you have events, new file has been written, and you want to somehow store that data in DynamoDB, you may need a Lambda to manipulate the data between these two steps. And every step can then trigger one or more additional steps. Like and we will come later to this approach. You will see it a lot when working with serverless. You have always some kind of triggering, some kind of pushing data from one place to the other. Let's see that in action with an IoT example. So imagine you want to implement an IoT temperature sensor. You want to have an app for that device. Using that app, you want to see the current temperature of the room where that device is, and you want also to be able to see the history of temperature changes. Maybe also you want to see history data about, like, I don't know, how often something happens or like the average temperature in that room. How do you do that using serverless technologies? The first thing is to implement the IoT sensor, which is a device, and to connect it to the IoT core, which is AWS offer for IoT devices. So it's an MQT broker, and your device is connecting to it all the time, maybe only when something happens. We will come later about how that affects your bill at the end. But your device is connected to that IoT backend. It's sending messages, maybe every 10 minutes, about the temperature, the current temperature you are having. And then now we start, okay, we want to do something with this data. The first thing you do is to implement an IoT rule. An IoT rule is kind of routing, which says if a message arrives, please forward it to that Lambda or to something else to do something with it. So we say, okay, if a message arrives with temperature in it, forward it to some kind of a Lambda to maybe to manipulate the data and then persist the data in a file on S3. Possibly like using also different services to batch this data, maybe using a firehose, which is like for processing data on the fly. And then you may want to push that data into Redshift to do some other business and analytics on that data. And now we have like maybe a different scenario or different use case. We want to send alarm if the temperature exceeds one threshold. Again, we have a different rule which says if temperature is higher than 40 degrees, maybe notify everybody before it's then too hot. For that, we have a different rule which triggers a different Lambda, and then we use SNS for that. SNS is a simple notification service which is responsible for either having like a fan-out pattern to trigger multiple Lambdas or even to send push notifications to mobile app. And again, with a different IoT rule and a different Lambda, you store maybe the last temperature so it can be shown on a mobile app. Okay, so yeah, maybe I was too fast. Okay, so that you see, the whole application can be implemented using almost serverless technologies, except for the Redshift in the middle. That's not serverless, but even with that, like if it depends on your use case, you can do use a serverless for that. But we have like implemented everything, every path of this data separately. They are very independent, so you can modify any path of this data without even touching the other path. It's very independent of each other. So let's see now for a developer. It makes sense. Maybe you like to work with serverless. Maybe it's a cool technology, but why should a business use serverless? Why, like it was in our case, a good match in the beginning? The first point is that serverless has an accurate cost estimation. And here I'm not saying serverless is cheap or is cheaper. I'm saying it has very accurate cost estimation or cost calculation model. Let's imagine this part of the system we've just talked about. So where we send an alarm. So if we want to say how much does that cost us, we know exactly how much we pay for an MQT connection. Like we know, okay, if a device is connected to the backend, we pay per minute. If like only it connects whenever something happens, we can reduce the cost, but we know exactly like how much does that cost us. We know for the IoT rules how much an evaluation of that rule costs us, and if a IoT rule triggers something, we know also how much we pay for that. And that goes all the way down also for the lambdas, for SNS. We know exactly like we pay per request for a lambda plus how many milliseconds that lambda will run. So we can say this path of data will cost us like exactly that. Having some assumptions like, okay, we need to make some assumptions. This device maybe send an alarm once every month, but sends a message every 15 minutes, so we can know exactly how much that path will cost us. You do that for all paths. You have maybe an estimated lifetime of that device, so you know how much this device will cost you in the future, which means you add that cost to the manufacturing cost, and you know how much this device should cost when somebody buys it. So that was the accurate cost estimation. The second point is shorter time to market, because like everything I have talked about, you didn't see like now we need to figure out how the scaling model works. We didn't need to figure out where we run that. We didn't figure out like how big or what kind of MQT broker we need. Everything of that is already has been taken care of. So that's why it's you can focus on what matters, on the business logic, on what you want to do with your data, and which means you can release faster. And also it's a reduced risk, exactly for the same reason, because we will not fail because the operating team has failed. We will not fail because our system doesn't handle that much of data. We will see later that there are some limits and you can reach them and how to work around them, but generally speaking, you have like eliminated one factor of failing, and that's always a good choice. So now I come to some list of do's and don'ts, and they are like, they come out of some specific experience. So I'm not here suggesting that it makes sense to do all of them in any product. But they all have reasons, and they all come from the nature of serverless technologies, which means like if you understand them, if you understand where do they come from, if you understand how to work around them, they will always be helpful for you. So as I said, take them with a grain of salt. They are not meant to be valid for every situation, but the reasons behind them are usually valid. First is a don't use Lambda for long-running calls. And like if something will take very long. Why? First reason is because you also pay for a Lambda, for example, even if it's waiting. Like if you have 1,000 Lambdas waiting for something to happen, maybe some data to be available, you are paying for every single one of them. A Lambda cannot do anything in this time. It's waiting for data to be there. So it's a cost question. Like whereas if you have a server and maybe you have a lot of calls which are waiting, your server can handle maybe more requests. That doesn't apply in serverless in a Lambda scenario. You have also limited concurrency, which is like sounds funny. I was talking all the time about how much does that scale, but at the end, there is a maximum number of concurrent Lambda execution in a region. Like it's 1,000, 2,000, 3,000, depends on the region. But if you have like 3,000 users all connected to a Lambda, and this Lambda is just waiting for something to happen, nothing else can be done at that time. And then there is also a hard limit on how long a Lambda will run. It cannot run more than 15 minutes. So if you don't know have to handle big data, or you have a lot of data to read and write, and that will take more than 50 minutes, and maybe a serverless approach at that point is not workable for you. Maybe you can divide this data and then use multiple lambdas, but without any kind of workaround, that will not work. Which then brings me to the next point. It comes also from the same limitations. Push, don't pull. Again, if you're waiting, you are wasting money. And you have limited concurrency and duration, so it will not work. What to do opposite to that is to push. Like if you have something which is a complex workflow, you have a pre-processing of some data and then doing some call, and then after that call has finished, to do some post-processing. Maybe divide that into 3 steps, like pre-processing, and then push the data to the party or to the Lambda or whatever will be processing that data. Whenever the data has been processed, let it be pushed back to you, and then do something with that. And for doing that, you can use a lot of also serverless products on AWS. So simplest one, of course, and the known one is to use SQS, which is a message queuing, like just write a message into a queue. But you can also use a file system if you want to write a file, and that file will trigger something. Like you can also activate events. So a new file has been written with this data. Maybe you want to call a Lambda with that content to do something with it, and that works for many other examples, like webhooks, call some other server, or a different Lambda call, or other stuff. And that also works for user interaction. So if you have a user which is waiting for something to happen, and that usually happens a lot when you are working with real-world devices. So network is always slow, it's not reliable. Like if you have a device and you want to control it via your mobile phone, that will take a few seconds. You can do that with milliseconds, because you want to send a message to the device, and the device needs to report it back. And sometimes these devices are in the basement, don't have good coverage. So that will take. If you want just to leave the connection open, that will cost you a lot, and you may run into timeouts. The best solution is that send something to the server, you get 202 accepted, maybe, and the result will come later via WebSocket. Maybe you also do the push with the WebSocket, depends, of course, on the use case. So what are triggers? Like I have mentioned already a few of them, but like what can trigger a Lambda or a different serverless product? One is an HTTP request. Either like directly you can say this Lambda can be called by an HTTP request, or you have an API gateway which does the routing for you and then calls some kind of a Lambda. But that's always like a solution. A different Lambda, like of course from your code you can do whatever you want, including calling a different Lambda synchronously or asynchronously. Like also both is possible. DynamoDB, which is, as I said, it's a kind of a database, a document database, and it has a very powerful feature. Whenever you write something, you can activate for that table the data stream, which means all changes will be then streamed to whatever you want. I mean, it can be streamed also to a Lambda, and that's like represents some kind of save point, like in a game save point. So you have saved your word to a Lambda, and then you trigger the next workflow. Save the data there, and then maybe some other party or some other part of the system will be responsible for validating this data, or creating an email, or doing whatever needed to do. F3, exactly the same. You write a file to some place, and then that triggers a Lambda or triggers whatever you want to process this data. Event bridge, also kind of SQS, event bridge, SNS, which are very different solutions for handling events, either in a persistent way, like in a message queue, or an event bridge, or SNS. Very similar, but the idea behind that is that you write a message somewhere, and getting published to a different receivers, and of course many others. So actually, I think there are multiple hundreds of stuff that can trigger a Lambda. Okay, now I come to also a very important point. it's about the latency of a lambda, like when lambdas should not be used if you want a guaranteed response in milliseconds. But before I can talk about it, we need to understand how scaling works in a lambda environment. So imagine we have a lambda which is being triggered by a HTTP request. So in the image we see, we have one request which maps to that lambda, and then at that point it's a fair score, so we don't have any lambda already in the memory, which means we have to start a new one. AWS will manage that for you. It will start like a lightweight virtual machine. It will download your code, which you have provided for that lambda. It runs the initialization code, which you provide also in your code. And then that all goes into the init phase. And then the handler will be called, which means that the code that will be run every time an event will come. Sometimes it's like here, you have a small initialization phase and a big invocation phase. Sometimes it's the other way around. And that depends on many aspects, like the language you have written your lambda in, the size of your code base, and many other factors. If we get another request at the same time, it will not wait for the first request to finish. Another lambda will be started. And that happens like for any request while we don't have an idle lambda to handle that request. Which means at this point we have 5 requests and 5 instances of our lambda in memory. Later on, we get maybe some additional requests, but the first 3 requests are done. So these requests can be handled by the same instance of the lambda, which means now we don't have initialization phase. We run directly in our handlers, which means if our handler is doing well, we can get a result very fast. And at some point, the 4th and 5th requests, these lambdas or the instances above, they have been idle for some time. Sometimes it's only 1 minute is enough, but at some time they be then unloaded, which means if we get a different request, again, we will have to go through that init phase. And that brings us to the point, if you want to have a very low latency, or at least guaranteed latency, possibly lambda is not the right solution for you. The init phase, as I said, it depends on what you do with that, but it can be up like to 1 second or even more. And it's not possible like to say, okay, I will call this lambda and then it's in memory, and then every consequent request will work with an existing lambda after 1 minute or possibly more, but there's no instance more in the memory, and then you have again to go through the init phase. There is something which is called provisioned concurrency, which may say, okay, I want always to have 5 instances of a lambda in memory, and that could help. But it also has some limitations, so let's have a look into them. Why we need them? So some like we have seen for lambda, it's the initialization phase, but also for some other services, they handle burst poorly. Even like the most scalable service, which is DynamoDB, which always has like good performance. If at one point like you are not using it and you have like 1,000 requests to write data into it, some of these requests will fail because it doesn't scale that well. It needs time to scale up. And for that you have provisioned capacity, which works with Lambda, with DynamoDB, but also with other solutions, and also can be modified by the scheduler. So if you know, okay, my devices connects all in the mid of the night to send data at exactly 2 o'clock. Maybe you scale up your database. You say, okay, now I need more provisioned capacity for my lambdas, more provisioned capacity for DynamoDB, and then scale them down after you're done. But it has a very important drawback. It defines a pay for usage model. Now you are paying for hour. The more, the less. The more you provision, the more you pay, even if you are doing absolutely nothing with that. So it's a trade-off. Sometimes it can be helpful in some scenarios, but you are losing something for that. Let's have a different look into the whole lambda and how they are called. As I said before, a lambda can call a different lambda, which means also like that lambda you can call a different one, and you may end up with a chain of calls, especially if you are waiting for a response. So I'm here talking about synchronous calls, not just triggering a lambda to do something else while the first one has done working. In this case, you will amplify the call start time, because if the first lambda has an init phase, calling a different one, and the second one has also an init phase, and the second one is calling a third one, and so on. Every one of those may have an init phase. And the issue is that now you are paying even for the init phase of different lambdas. Like if the first one calls 10 lambdas, and it's paying for the time it's waiting for the second lambda to finish the init phase. And it also breaks isolation and independence. So we are, like in this conference, have now seen that multiple times. In one talk about advanced API usages. So try to avoid that. If you have something which calling something else synchronously waiting for data, and again that one is calling something else, that's probably not a good pattern. Maybe you have to remodel your application. As a rule of thumb, but it's just rule of thumb. It's not like something you have to do. If one lambda is calling a different one, it's okay, but if that gets more and deeper, maybe you should restructure your data or structure your program. Let's sum up how that works, like how the whole scaling, how the whole lambda auto-scaling works. So what you have is auto-scaling single request application. Like you can, if you have a lambda which handling one request, you can do a lot of stuff in that lambda, but you can't handle a different request. So you need always to keep that in mind. You have an upper limit on all number of concurrent lambdas in any region. No matter, like you can, sometimes you can increase that if you asked for more, but at one point it's always there's a limit and you can't get more. So you can't just run as many lambdas as you want. And you have the penalty for the initialization fees. So always keep that in mind when you work with lambdas. Sometimes to work around that, you can batch and throttle, which means like if, for example, if you have a queue, instead of calling one lambda for every message, you can tell it to wait until you have 5 messages and then call a lambda. That may help sometimes, especially if you are not requiring a response immediately, which you shouldn't be doing when working with queues anyway. So that may be a viable solution. The gist of that, don't try to work around it. Like if you have a lambda which is waiting, don't try to do some other stuff in the which are not related. Don't try to handle like a different request. You know how that works. Try just to embrace it and to use it in the way it was supposed to be used. The next step or the next do's is that which I call everything as a code. I don't know if it's anybody call it this way, but it's like even more than infrastructure as a code. So we have seen you have your code, you have your lambdas, you have a lot of resources like a database or a connection between the lambdas, the permissions, everything, and it can get complicated. It's be like a big jungle of resources. So if you want to be able to restore the system to any point or to have like sane deployment processes, you must use infrastructure as a code as a code, and everything else. Oh, what did I do? Okay, wrong button. So it goes for code, for infrastructure, for alarms. We will see that later. Alarm and monitoring is very important when working with serverless, and also for the documentation. We use for that like one pull request, so anybody who change anything must put everything in one pull request. Like it's not enough to modify the code if you have to change something in the infrastructure. Don't have invalid states in your repository. If there is something, any state, it must be deployable, which means deploy like pull request for everything. What you can use to have some kind of organization, so like you can put everything in the same place, and you will need to figure out which lambda is calling what. But you can also use stacks and applications, which are like terminology coming from CDK and then from CloudFormation, which is the way how you deploy application AWS. But it's kind of organizing code in parts that can be deployed separately. Again, come to something which is relatively new, like it's been now, I don't know, a few years, but it's a very important feature which advertised as low-code solution for creating workflows. On the official documentation, it says it works with more than 200 services and thousands of APIs. But it's also very important if you only use it with calling lambdas. It's called a step function, which, as the name says, it's a way for organizing workflows. You can, for example, use it for error handling and retries. So if you do something and expect it to fail, maybe you want to try it 5 times and then fail after that works. It doesn't work. So, for example, if you work, again, example of working with a physical word device, it may not be there, it may not be connected. So maybe you need to try that few times before you give up. You can use step functions for that. It can be used also for parallelization, which means like call 2 lambdas, wait until the result is there, and then do something with the result of both calls. And also generally for stateful workflows, like if you want to implement the Sega pattern, whatever, something started manipulating data and at the end you have some result, can be used for. One way to use that is also for delays, which is like a very complicated thing to solve in a serverless world. You wouldn't imagine that, but if you have nothing running all the time, it's very hard to say wait 5 minutes and then do something. Like usually you have to do some workarounds around that. But with step functions, you can say, like we have only a step function which says always wait something and then call a lambda. We give it the payload, it's a lambda, so we can do a lot of stuff with that. Just say wait and then do something. Try to avoid heavy startups, like a big time, how to minimize that initialization phase. First thing to do is to avoid like using many libraries, big frameworks. Try to keep your code very compact. That means, for example, if it doesn't make sense to have like big independence injection libraries in the code you deploy to a lambda. It doesn't make sense to have a big routing mechanism behind it. Maybe outsource that routing to API gateway, which is a serverless solution. So whenever a request arrives there, it's already has you know it's meant for this function, and you don't need to do all of that. Something's wrong with this one. Okay, reduce the package size, which means remove everything you don't need. Like even one important aspect of it is that reduce the initialization phase. And also it means sometimes you are paying less because then the lambda will work. If only less by a few milliseconds, if you have like billion call of that lambda, it will add up. So try to reduce that. Maybe remove the AWS SDK because it's already provided to you by the runtime. So remove everything you don't need. Do a shakedown and everything which is left out, remove it from the deployed package. And initialize only what you need. If you, for example, start your a lambda function, don't get every configuration from the database, because this lambda function may only run for one request and then be unloaded. So you have like retrieved big data from a database which you don't need. But also on the other hand, if you have retrieved something, keep it in memory. And this comes to like a very common misunderstanding of lambda. Lambda is not stateless. If you have a lambda and you have a lot of requests, it's very possible to use the same runtime. It's like the global variables will be the same for many requests, which means if you have already read some data from database, keep it in memory and you can use it later. This point is about like where does like what's the purpose of one lambda, and we like to consider it as a domain boundary. Whenever you enter a lambda, you enter it like from somewhere, we don't know where, and that's why we always do input sanitation. So it could be that your lambda is being called by a different lambda, but also possible that this lambda is changed later and somebody is calling it from an API gateway, which means you get user input without any validation. So always don't trust the input. Always consider the data you are receiving to be dangerous. This one is maybe hard to do, but yeah, if you try, it's possible, consider it as an independent component, and it also will reduce the factor which can go wrong. So if in your application, so if one lambda fails, maybe that's a delay, but like you should not the whole system should fail with that. And you should also have clear data ownership. Like that part of the system belongs to this lambda or this lambda. So if you have multiple lambdas for reading, writing the same data, you know that data belongs to them, but nobody else is allowed to change that. That will help later if you want to modify the internals of that lambda. That will help to avoid breaking different systems. And yeah, the last point is just saying this one is not easy to achieve. Like you will start with this design, need to change it later, but yeah, that's like what you always do. Expect errors because you are working with a highly distributed system. So it's by not everything is inside the same process. You are pushing data somewhere and you hope it will arrive. Lambda may have changed in the time. Maybe it was working when the time when you deployed yours, but it changed later. So always expect to have some errors, and you should work around them. So if something is not working, if the database is not there, if you have a throttling error because there's no instances available to do anything, expect them. Maybe you just a retry, or maybe just write this data in a dead letter queue, because if you have, for example, a lambda which gets a message from an IoT device and it fails, and you don't store that message, then the data is gone. Like there's no way to retrieve it. So use a dead letter queue, which can be configured very easily. If a lambda fails, the data will be written somewhere. You don't need to do a retry on that. Maybe it can be done later manually, like, I don't know, reprocess all this data, but at least the data is not gone. Come here to a point which is important. Aim for idempotency. If you don't know what idempotency is, it comes from linear algebra, which means like a transformation in a vector which can be applied multiple times without changing the results. Like if you have some, I don't know, vector and you apply a transformation, like a projection. So if you have a vector and you get only the x component of it, and you do that 10 times, you will always get the same one. So it doesn't matter if you project it 2 times on the same axis. In computer software, it's not as strict, so it doesn't have to be exactly the same result, but it has to be a result that's not completely different. And the reason for that, why we need that, especially when we are working with serverless technology, is that we have loose guarantees. Like as I mentioned before, a message in SQS may be processed multiple times. A message coming from MQT broker, like an IoT message, also it doesn't have the guarantee to be processed exactly once. The best you get is at least once, which means like one message can arrive multiple times. Additionally, like in a distributed world, you don't have transactions usually, so you can do half of the work, then fail, and then you maybe try that, and you do the first half again. So only at least one delivery. So you have to be prepared for that, and the way to be prepared for that is sometimes very complicated, sometimes very easy. If the action is sending a message to a device to close the valve, if you do it twice, nothing will happen, like the device will be closed twice. If you are sending a push notification to a user, probably you shouldn't bother him, especially if that happens not twice, but 10 times. So it depends about the use case, but yeah, keep that in mind, that could happen. And a different property which you should always do when working with serverless is to monitor everything. You should monitor errors. Like we have seen, there are a lot of steps, and if an error happens in any step, like the caller or the data where that started, will not know that, because everything is asynchronously happening. And like if you don't want to go through every logs and watch for yourself if something was wrong, you should monitor errors in every service. And also it's useful to monitor under and over usage. So let's say if you have, let's take the example of DynamoDB again. If you know, I get data and I have usually about 10 to 20 read units every hour or every second for that table. So maybe you can then create an alarm which will notify you if you have only 5 read capacity, which means if you're reading less than usually do, maybe something went wrong, maybe some kind of a routing is not working and the data is not getting there. So you can also do that. So sometimes errors are not just exceptions in the logs, sometimes error manifested by something not being called at all. You can also set up alarms based on business logic. So if you, example, expect to have a new device, 10 new devices every day, if you have only 5, maybe you should then also be notified something is wrong. And you can use logs to correlate or domain identifiers to correlate logs, which means if you have a long system where message arrives at one point and then it's being processed by multiple handlers, so how you want to know which one has caused this error. Sometimes it's something at the beginning. If you don't want to use very expensive services like X-ray, maybe you can use a domain identifier and then you'll be able to correlate the different logs of the different services. Integration tests are very important because there are a lot of places where you lose control over what's happening. You push a message to DynamoDB and then you expect it to appear somewhere else in a different place. So it's ideal actually for doing unit tests. You have very small piece of code which you can test. You know what the input, what the output is. But the errors may lay somewhere else, like if you push the wrong data and some kind of service doesn't work with that. So you have a lot of touching points with the not operating system, but with other code that you don't control. So you have to do an integration test. That can be also easy sometimes. So if you have done everything, as I said before, having infrastructure as a code, being able to deploy every pull request to a testing environment, that could work very well. Use the ICD pipeline to deploy on every pull request. That will help you. One thing what you shouldn't do is to use be very easy with the permissions. That will clarify the responsibility of the data. So we're back at the point where every part of the system should own this data, or should be clear what it's supposed to call, and that will help if you use the least privilege principle, which means give every part of the system only the permission that it needs. If you have one Lambda should be one role, and a role is in AWS is like the permission that Lambda will have, the identity it will assume when it's run. So it's basically speaking just the permissions. And avoid using wildcards in policies. Policies are the building stones for the permissions for the roles. So if you here look at the picture, you see two examples of the same policy more or less. So if you have a Lambda which needs to read device data from DynamoDB, one way of doing that is on the left to say action is an asterisk. I am allowed to do anything with that Lambda, include that database, including writing data. And at the resource part of the policy, you see at the table /**, which means do anything with any table. That could be rewritten in a very specific way on the right to say the action I need to describe table, query, and scan, like to get data, and I need access only to one table. That will help later to clarify also who's responsible for what, and not to delete or add data by mistake. Serverless can be added to existing applications. And like in our case, we didn't have that, but as I said in the beginning, some part of the system could not be done with serverless technologies at the beginning, but were possible later. So it's not a binary choice. You don't have either serverless or don't. Like use it whenever it makes sense. You can improve your application over the time. Is it either because you learned better or there are new technologies? So it's not your grandpa's serverless. What was possible not possible at one time, maybe possible now. The takeaways, this is the last one. So if you forget everything which I've talked about, what are the ideas behind serverless? So serverless trades control for convenience. You get a lot in return, but you lose the control. So if you need very specific situation where you had to take actions to do very specific stuff, then maybe serverless may not, or Lambda specific may not be for you. It's not about being cheaper. It's about having accurate cost estimation. It has improved a lot over time. So if you tried it once and didn't work for you, it doesn't mean it will not work now. So maybe give it a next try with your next product. Just try it, or maybe just have a look into what you can do with that. And at the end, it's not silver bullet. So don't feel ashamed if it doesn't work for you. It's not meant for every use case to be done. And with that, I've reached the end. Thanks a lot. Thanks for you visiting my talk. Hope you liked it. If not, please tell me. If you like it, please don't forget the green papers. I think the printer ran out of green ink, so there are some other colors, but not important. Thanks a lot, and enjoy it.